Hi folks, we're going to take a look at number 11 from page 213, and what they want us to show is that a cubic function has a single point of inflection and that the slope of the tangent at that point is given by this expression here. Okay, so we know that we look for points of inflection where the second derivative is equal to 0 or doesn't exist, although because this is a polynomial, we know that the derivatives are always going to exist, so we don't have to worry about that. We're just looking for where the second derivative is equal to 0. All right, so let's start by finding the first derivative. So here, a is just a constant, so it's just a times 3x squared, so 3ax squared, plus, again, b is a constant, so derivative of x squared 2x, so plus 2bx. Here, c is just a constant, derivative of x is 1, so plus c, and the derivative of a constant is 0, so that disappears altogether. All right, so now let's find the second derivative. So here again, 3a is just a constant, so 3a times 2x, so that's going to be 6ax plus, and again, 2b is a constant, derivative of x is 1, so plus 2b, and derivative of c is just 0. Okay, so what we need to do is determine when this second derivative is equal to 0, and so we can just solve for x here, bring the 2b to the other side, so negative 2b over, divide by 6a, and we can simplify that to negative b over 3a. All right. Now keep in mind that this is not enough to show that there's a point of inflection. All we know is that the second derivative is equal to 0 here. We have to show that the concavity actually changes at this value. All right. So let's draw our number line here. So the only place this can change sign is at negative b over 3a. So how can we show that it does change sign? Well, let's take a look at the second derivative. The second derivative is just a line, because remember, 6a and 2b are just constants. So this is just the slope. This is just the y-intercept. So we know that a line will cross the x-axis. Now, if a is a positive number, meaning the slope 6a is positive, we know it's going to cross from negative to positive. And if a is negative, meaning 6a is going to be negative, then it just goes from positive to negative. Okay, now for a point of inflection, it doesn't matter which direction it goes, but we know for certain that the slope, excuse me, that the second derivative does change sign across this point. So therefore, x equals negative b over 3a is a point of inflection, and in fact, it's the only one. So there must be one, and there's only one of them. All right, so now they want us to show that the value of the derivative at negative b over 3a is given by this expression here. So I'm just going to have to do some algebra and input this into our first derivative. So y prime at negative b over 3a is given by, so 3a times x squared. So 3a times negative b over 3a squared. And then a plus 2b times x, plus 2b times that value, negative b over 3a, and then plus c. All right. So like I said, looks like it's just going to be a whole bunch of algebra. Now here, again, very important that we put this expression in brackets, because when we square this negative, it's going to become positive. So here we have 3a times, this is just going to be b squared. Okay. Now, I'd be tempted to write this as 9a squared, but since I've got a 3a in the numerator, I'm actually going to just leave this as 3a squared. I think it's going to make my life easier when I have to simplify. Okay, and then here I'm adding a negative, so minus, and it looks like it's 2b squared over 3a, and then plus c. So here, as I notice, this 3a reduces with one of the 3a's in the denominator, so I'm left with b squared over 3a minus 2b squared over 3a plus c, and of course these are like terms. Okay, so b squared over 3a minus 2b squared over 3a is just negative b squared over 3a, and I'll just write it the way they did it up here. That can be written as c minus b squared over 3a. Okay, and so we've shown what we needed to show. So the idea here is that we were working with a general cubic function. So anything we established means that it works for all cubic functions. So we just found the first derivative, being careful with our constants, found the second derivative, showed that there was only one zero because the second derivative is linear. And that also helped us show that the sign had to change regardless of whether the leading coefficient A was positive or negative. And then from there, determining the value of the derivative at that point was just a matter of being careful with our algebra. Okay, that's it for this one.